very honored to be here, and just slightly disappointed that I have to talk in a geometric analysis section after Yao, Shen, and Rick and Toby. But it's a manifestation of the fact that a function on a finite set always has a minimum. So on the other hand, Rick actually introduced a lot of stuff already, which would make my job easier. So let me start by reminding you what the plateau problem is. So this will be the subject of my talk too. Okay, so he already introduced the very general version that I'm going to be interested in. So we have some contour sigma. Actually, let me call it some contour gamma inside some ambient space sigma, and gamma is m-1 dimensional. And I'm not going to be too specific about what I mean by this contour. I mean, if you have a one-dimensional, if m is equal to 2, then you can really think about a simple closed curve, okay, which is small. But maybe you want to be more general. And then you have an ambient sigma, and sigma is an m plus n dimensional Riemannian manifold. Think about it as smooth as you like, probably even closed if you want. I mean, it's not necessarily going to be closed. You can maybe just assume completeness, but if it's closed, it's maybe going to make my life easier. Okay, and it was already mentioned that so this raises a series of questions, and the first question is what we should understand as okay, so what is the plateau problem? Then of course, I mean, the question is find the m-dimensional or an m-dimensional surface which spans gamma and minimizes the m-dimensional volume. Okay, so that is the question. And it was already mentioned by both Rick and Toby that a fundamental question which arises is what do we understand with the words spans? What actually are exactly the class of surfaces that you want to consider? And what do you understand by m-dimensional volume too? So that is the problem of existence. So that is the first problem. And then once you actually tackle this problem, for which you can actually give several different frameworks, there's a second question, which is the question of regularity. And now the question of regularity actually bifurcates into two sub-questions. So first of all, how regular is your solution when you are far away from the boundary? And that's interior regularity. But then the other question is how regular is actually your solution at the boundary, and how do you attain the boundary condition? And that is the boundary regularity. And the punchline of this talk is that while this one is certainly not a finished story, we have quite a lot of understanding in most situations. This one is much more open. And in spite of the fact that there's been a lot of mathematics that has been invented to tackle this problem, there's still a lot of mathematics that has to be, there's still a lot of other mathematics that has to be invented to go further. Okay, so before I talk about regularity, though, let me review a little bit about existence. So it was already mentioned that there are several answers to the question, in which class of surfaces do we want to minimize this? And let me kind of argue that there's not a correct or wrong answer. It depends somewhat on what is actually your goal. For instance, if your goal is trying to model soap films, then you definitely want to go into certain directions because you do know, for instance, that soap films develop singularities in real world. So then therefore your model should try to capture those singularities. But if you're, for instance, interested in like finding canonical representative in homology classes, like it was mentioned by Rick, then probably singularities are not desirable at all. And so this actually leads to different approaches. And okay, I know I shouldn't be doing philosophy. I already actually did it on Monday, and this was maybe a mistake, but let me do a little bit of philosophy over here. So you can essentially identify three very broad classes of approaches to existence. So the first one is what goes under the name of parametric approach. And this was already touched upon by Rick. It was pioneered by Douglas and Rado, who solved it, who used it to solve the two-dimensional plateau problem in R3. And they were able to prove that if you have a curve in R3, there is a disk which minimizes the area among all disks which are spanning this curve, under understanding this appropriately. Actually, I mean the way this is really done is you look at maps which go from the disk into R3, which reduce to an homeomorphism of the boundary of the disk onto the curve, which is your kind of fixed boundary, and then you minimize the area of the image, and in doing this, like by making conformal paternization, you actually reduce it to minimize the Dirichlet energy. Okay, so that is the parametric approach. So this was pioneered by Douglas and Rado, and I'm just going to mention very little about it, but I'm going to mention something. So then there's what I would actually call the set theoretic approach. Okay, this is really kind of my name for it. Parametric approach is an accepted terminology in the literature. This I'm essentially coining it. So by set theoretic approach, I mean what actually was pioneered by Reifenberg. So in the set theoretic approach, you're just saying like, okay, any closed set in my ambient space is actually an additional surface. And what do I use to actually measure the volume of this closed set? Well, I can use the Hausdorff measure. Okay, so that is a very well accepted generalization of the differential geometry area of the submanifold. So now what it means though to span somehow the curve under this, where you're just going to put some topological assumptions that essentially the curve is trivial in some sense in your closed set, okay? And then you just try to minimize in this class of sets, okay? And this can be done in several ways. So Reifenberg is an example, but it's not the only example. Okay, and then it is what I would actually call a functional analytic approach. So functional analytic approach is actually going like more or less this way. So you kind of select a class of desired object. For instance, let's say if you're like thinking about the theory of currents, the theory of integral currents, what you're actually going to do is you're just going to take singular chains with integral coefficients. Okay, so these are like formal union of finitely many images of simplices, and then you just attribute a you map them into your problem, so you have an orientation, and then you decide the multiplicity for all of these pieces. So you would actually like to have some sort of theory which is minimizing it in this ambient, but this one is not compact, so you compactify in a certain way, and then you hope after the compactification that your area functional, which is well defined on these objects, extends to something which is lower semi-continuous. You sort of take the lower semi-continuous envelope. And if you have compactness properties, you actually apply the direct methods of the calculus of variations to find the minimum. Okay, so an example of this is the Federer and Fleming approach, which was already mentioned by Rick, which gives you integral currents and which allow you, for instance, to say that you can recover integral homology of manifolds using this theory, and in every homology class you actually have a minimizer in this functional analytic setting. But there's several other things you could do. For instance, you could actually do homology with different coefficients when you're doing the functional analytic approach. Actually, predating the Federer and Fleming theory, there's the theory of De Giorgi, in which you're just minimizing among boundary of sets, which you can think about the subset of the Federer and Fleming theory but you can also think about it as a category in itself. Okay, so in all of these situations, you actually have very well-established existence theories which deliver an object, but that object is often quite irregular to start with. And it's actually quite funny to see that when, for instance, you consider interior regularity is essentially completely solved in the Douglas-Rado situation, but boundary regularity is not. So there's a very famous open question, and this is the following. So are there boundary branching points? So branching points would be singular points for the Douglas-Rado solution in R3 with a smooth boundary. So this is still actually an unsolved problem. It's maybe the biggest open problem in the area. So that is an unsolved problem in the first case. There's another unsolved problem actually on boundary regularity. So if you take the set theoretic approach, pretty much there's actually many ways you can actually define what is your class. And there's Reifenberg, but there are other proposals. There's one by Guy David, there's one by Jenny Harrison. So there are several, but they all essentially land into a class which are called Almgren minimal sets. And there's a very powerful theorem by Gene Taylor, which tells you that if you take in the interior an Almgren minimal set in R3, so it's either smooth or it might have singularities, but the singularities are completely classified. So locally, your solution is going to be diffeomorphic either to the union of three half planes which join at 120 degrees, or you're going to be diffeomorphic to the cone which is constructed over a tetrahedron, right? So it's completely classified. But R3, 2 dimensions in R3. Yes, it works for 2-dimensional surfaces in higher codimension, but there's no parametric approach which goes beyond 2 dimensions. Okay. So the question is, which is still open, so is there an equivalent of Taylor's theorem at the boundary? And there are some results by Guy David, but and by Allard, but it's widely open. So just what I mean by a Taylor theorem is a complete classification of all possible singularities that an Almgren minimal set could actually have at the boundary. Okay, so but I should have started the clock on the 40 minutes, but I actually forgot to start. So okay, how much time did I use already?
So you've used 13 minutes.
13 minutes. Ooh, wow, too much. Okay. Well, okay. Let me start the clock at 27 minutes now. So what I'm actually going to talk about is about the functional analytic approach. Okay. So first of all, let me mention a theorem which is the summary of the collective efforts of several people, and so I'm not going to give up attributions, but it's a very important theorem that I want to mention in the interior. So this is for the interior regularity. Okay, so interior singularities, first of all, exist. So interior singularities in the Federer and Fleming theory can occur. But so in codimension 1, the singular set has dimension at most m-7. In higher codimension, it has dimension at most m-2. And then in both cases, it is respectively m-7 and m-2 rectifiable, which means that they're very close to BC1. But certainly in the case of higher codimension, there might be fractal singularities, and there's very strong suggestions that there might be fractal singularities even in codimension 1. So let me just say, but possibly fractal singularities of lower dimension occur. So in fact, in higher codimension, this is really a theorem, although the singularities are kind of special. Let me not touch on to this. And for hypersurfaces, this is really proved that there are fractal singularity for stable objects, which were touched by Rick, but they are not been. It has not been proved that they are minimizing. Okay, so in a sense, there's a kind of very good understanding. But let me actually see what happens at the boundary. Okay, so at the boundary, for boundary regularity, there's first of all a very fundamental theorem, which was first pioneered in his PhD thesis in 1969, and then later extended in his Anna's paper in 1974, I think. So there's a great theorem by Allard, and I'm actually going to give you not the one in the thesis, but the one which is most general in the paper, which appeared later. And the theorem of Allard essentially says the following. So at a boundary point, pretty much any reasonable notion of stationary solution. So pretty much everything that we covered so far, but actually much weaker, just to be stationary in the sense of a critical point of the area functional. So at the boundary point P, a stationary integral varifold that's the technical notion, which is sufficiently closed. So which is sufficiently close at some scale to a half plane is in fact a smooth minima surface at a slightly smaller scale. Okay, now, of course, like I should actually specify what I mean by sufficiently close, but there's a very elegant way of telling you what it means to be sufficiently close. And it means that it's just enough that say, when you intersect with a ball of radius r, the total area of your object is just a little bit above or not much larger than the area of half a disk. Okay, so sufficiently close means the following. So you have a small ball. So here you have your boundary. All the chalks are white. Okay. Yes, thank you. Okay, so here you have your boundary. And if your, say, surface over here or generalized surface has area which is less or equal than half plus some epsilon times the area of the corresponding disk, which of course is slightly more than the area of half of the disk, then you go at a slightly smaller scale and you're regular. Okay, and the theorem somehow, an aftermath of this theorem is also that your solution can't possibly pick up something which is smaller than half the disk, right? Because as soon as you drop a little bit below 1/2 plus epsilon, you actually have to be diffeomorphic to it. Wonderful. Okay, so this is a wonderful theorem, and it has, and this is already noticed in his paper. And in this way, he recovers a result that he had already in the PhD thesis, and in the special case of codimension 1. So a corollary of this, which is not an obvious corollary, I mean, it needs a little bit of work, actually. A corollary of this is the following. So if you're looking at a Federer and Fleming solution, so if the boundary of a Federer and Fleming solution lies on the boundary of U, for U actually inside Rm plus n, convex, let me say uniformly convex subset. So you have a picture like this. For instance, you have the sphere, and your curve is actually lying on the boundary of this sphere. And actually, the Federer-Fleming solution is going to be completely regular in a neighborhood of your sample, independently of what is actually the dimension and codimension of the surface. So the FF solution is regular in a neighborhood of the boundary. Okay, so this actually is fantastic news, because it means in a lot of very reasonable situations, you can actually solve the plateau problem. And in fact, it's even, the boundary regularity is even luckier than kind of the interior regularity. So if you have this convex barrier, there is no singularity at the boundary, okay? So what happens if I drop that assumption? So if I drop that assumption, then the situation is much more complicated. And the reason why it is much more complicated is because of the following example. So the Federer and Fleming solution has multiplicity, and there's something nasty that can happen, although it's extremely unlikely. So if I give you a boundary which is given by two circles which are oriented in the same way, and that's because when I am actually using the Federer and Fleming theory, there's an orientation which comes into it. So if I'm trying to solve it for two circles which are oriented in the same way, and they're lying in a two-dimensional plane, the solution is going to look this way. So it's going to pick this corona with multiplicity 1, and then it's going to pick the interior disk with multiplicity 2. So there's no way you can actually escape the situation. You could still say, like, well, my solution is perfectly regular, right? So I have essentially a unique surface which is going through sort of this inner boundary, and my multiplicity in this unique surface is actually jumping from 2 to 1, but the solution is extremely smooth. On the other hand, this type of example, which then, if you can prove that your solution always has a structure like this, it has to be a very unlikely situation, because your inner boundary has to be contained inside the minima surface which goes outside, right? And that is a very unstable situation. I perturb it a little bit, and all of a sudden, actually, these guys actually pop up. So this is the example, but it's a much more complicated situation. And there's a famous theorem by Hard and Simon in 1980s, which actually says that, again, the Federer and Fleming solution has full regularity at the boundary, but you have to understand the regularity in this way. So FF solution is fully regular at the boundary if you understand that two-sided situations like this one can occur. But only thing that can occur is that either your surface somehow ends up at your sample by taking multiplicity 1, or it goes across it, and then the multiplicity jumps by 1 once you goes across it. And somehow your solution actually completely includes kind of this inner boundary. Okay. There's one deus ex machina of this, which for the PDE experts is the Hopf maximum principle. So first of all, because you are in codimension 1, solutions of the plateau problem tends to be ordered, right? So they cannot cross each other. So that is a famous fact. And so in a situation like this, what actually cannot happen is that, like, you get a surface which sort of touches the other surface from above. So the Hopf maximum principle is actually telling you that that is not going to happen. So somehow it's the Hopf maximum principle which in a kind of curve situation sort of forces this picture. So this Hopf maximum principle is not correct in higher codimension. And it was an open problem for some time to actually get something which is even much weaker than that. So first of all, let me just make the following basic observation. So if you are in the Euclidean space and you have somehow a boundary, there's always going to be some sort of, furthermost point that you have. Like, for instance, you could take a very large sphere that does not touch your boundary, and you can shrink it by keeping it homothetically until it touches for the first time the boundary of your sample. Actually, Allard's theorem would apply in that case. So Allard's theorem has a local nature. That is a sort of corollary. But Allard's theory really tells you that if your surface, if your solution of the plateau's problem is actually all on this side, and it's taking your sample with multiplicity 1, then it has to be regular. So another corollary of Allard's theorem is that if you are in the Euclidean space, because you always have this convexity business, there's always at least one regular point at your boundary. And then, of course, there's a neighborhood of regular points on that regular point. But in a general Riemannian ambient manifold, you don't have this. For instance, if your manifold is closed, you're not going to have a foliation by convex surfaces. And that was a, okay, so a corollary of Allard is there is always at least one boundary regular point in any dimension and codimension in Rn. So if the ambient is Euclidean. Yeah. Yes. Sort of underlying, there's always that assumption. And a question by Angren was, is there something similar in Riemannian manifolds? So is there at least a boundary regular point? In Riemannian manifolds. Okay, and this was answered only much more recently. So we have a theorem joined with Guido De Filippis, Jonas Hirsch, and Annalisa Massacesi. So in higher codimension, we can at least prove that boundary regular points are dense. So boundary regular points are always dense. And that is a theorem which does not use this convexity argument. So it has to tackle also situations in which you actually have two-sided boundary points in higher codimension. And at first sight, actually, when we proved this, we kind of thought, okay, maybe the theorem is very suboptimal, but because of this Hopf maximum principle, you can actually make examples in which there is a minimizer which is bounding an exterior curve and an interior curve, and there's actually lots of touching points in a situation like this. there's lots of touching points, and we cannot make actually this lots of touching points just a set of positive measure, but we can make it actually a set of any dimension. So the result is optimal or almost optimal in the sense that so you can create or there exists boundaries which are smooth, so C infinity in R4, so they would be curves. Let me just put this here. There exists C infinity closed 1D submanifolds in R4 with a set of boundary singularities which has dimension 1. So really the optimality is whether you can prove, I would expect that they have dimension 1, but they have measure 0, one-dimensional measure 0. And that's like somehow the gap within this theory. On the other hand, it's not super satisfactory because the type of singularities that we have are really kind of like, geometric singularities in the sense that locally, I cannot describe my surface as being embedded, but, it's an example in which you have kind of an inner curve like this and an outer curve like that. And if you didn't have them together, each of them would bound actually its own area minimizing surface. And the only problem is that because I am in higher codimension, like, the inner curve can kind of go in and out of the other surface by using the higher codimension. And the minimizer is somehow kind of touching a lot of times the interior minimizer, the other guy. But somehow analytically, they actually decompose into two very regular guys. And what I would conjecture, and I don't know, is that this example is because I'm dealing with singularities which I would call not essential, meaning that I would still be able to decompose my solution into two very nice surfaces. And so my conjecture would be that essential singularities have dimensions at most m-2. Okay, so there's a lot actually to go towards that direction. I don't have the faintest idea on how to approach that. But let me mention now another example, which is kind of very, well, it was surprising to me, at least at the beginning. So an aftermath of the Hart-Simon theorem. So this is a corollary of the Hart-Simon theorem. So if I give you gamma C infinity smooth embedded curve in sigma three-dimensional Riemannian manifold, the Federer and Fleming solution has always finite topology. So it's actually classical, meaning that it is a smooth minima surface which takes the boundary in a smooth way. So a posteriori, it's actually a surface of finite topology. Okay, so here is an example. And this is due to myself, De Filippis, and Hirsch. So there exists a Riemannian manifold, so sigma, four-dimensional smooth Riemannian manifold. And gamma in sigma C infinity embedded one-dimensional curve. Sorry. Because you have a boundary, and your point is centered at the boundary, it's always half of the disk, right? I mean, okay, maybe I should have put here half disk, and then here I could put one. Okay.
5 minutes.
Yeah. Oh, yeah. The 5 minutes, 20 seconds actually over there. Okay, so there's a one-dimensional curve which bounds a unique Federer and Fleming solution with a boundary singularity, but most importantly, infinite topology. So the surface, the solution is really infinite genus. It's an embedded surface. There's actually no singularities inside. So as soon as you actually go a little bit away from the singularity, you just have finitely many handles. But if you actually converge towards this boundary singular point, you have infinitely many handles. And it's the unique Federer and Fleming solution. There's no other. So it's really something you have to swallow. And a very interesting open question. So this is a conjecture by White. So this cannot happen if you substitute C infinity with real analytic. So does not happen if sigma and gamma are real analytic. Okay, so then I have 4 minutes to actually introduce the very last problem. And the very last problem is also just like barely touched right now. So the very last problem is the following. Because I am actually allowed in the Federer and Fleming theory to give multiplicity, I can also give multiplicity to the boundaries. So one very interesting thing that I can say is I can take like a solution for 2 copies of the curve, for instance, in R4. And there's actually very surprising situations. So for instance, it doesn't happen that the solution for 2 copies of the curve is going to be 2 copies of the solution for a single copy of the curve in higher codimension. So this actually happens in codimension 1 in the case of hypersurfaces, because in some sense there is an ordering of solution, but it doesn't happen in higher codimension. So you would have, for instance, like, two, like a disk, a circle with multiplicity 2 who bounds actually a solution which is essentially a Klein bottle with that circle removed. Okay, so this is actually both asked by Allard and White in 2 different situations. And it is the following question. So can we establish a regularity theory when the boundary has higher multiplicity? When gamma takes higher multiplicity. And there is a first answer, and that is by White. And the answer is yes, in codimension 1, because it's a somewhat special situation, and it can decompose a solution which is taking like twice the boundary, essentially in 2 solutions which are taking the boundary singularly independently. And then it's again somehow the opt maximum principle, which is telling you that the 2 solutions have to kind of start with separate angles. But it's much more complicated in higher codimension, and there's a very interesting phenomenon here. So first of all, we have a recent theorem with Stefano Nardulli and Simone Steinbrücher. And that says, so if you have a 2-dimensional minimizer in higher codimension, the analog of Allard's theorem holds at boundary with higher multiplicity. So what does it mean? It means the following. If I have something which is taking a boundary with multiplicity, say 3, and I know that the total area is a little bit below 3 copies of the half disk, then really you actually decompose into 3 disks which are coming off either at different angles, or if they are coming off at the same angle, then they completely coincide. So it could be 2 copies of a half disk and 1 copy of a half disk, or 3 copies of 3 different half disks, or 3 copies of the same half disk. Okay, so there's a forthcoming actually theorem by a student of mine, Fleshler. So the same theorem is actually false. Oh, okay. So, but how do I actually cancel this guy? Stop. No.
Like stopping your car.
So yeah. I'm just going to state this theorem. So the same theorem is false for 3-dimensional surfaces. So in other words, there can actually be singular points under Allard's assumption, but these singular points are actually of lower codimension. But singularities of this type, so have dimension at most m-3. Okay, and well, that is really the end of my talk.